Let's dive into the fascinating world of data storage technology, specifically how your smartphone and solid-state drives, SSDs, manage to store massive amounts of information in such tiny spaces. It's mind-boggling to think that a device smaller than your palm can hold thousands of photos, videos, and apps. But the real magic happens at the nanoscopic level, where incredibly complex structures work together to make this possible. At the heart of modern data storage lies a technology called VNAND, or vertical NAND. These are essentially stacks of memory cells that store your data as tiny electrical charges. But before we delve into the intricate details of how these work, let's first understand how digital information is stored in the first place. When you take a photo with your smartphone, the image is broken down into millions of tiny pixels. Each pixel contains 3 values, red, green, and blue, ranging from 0 to 255. These numbers are then converted into binary code, the language computers understand, consisting of ones and zeros. For instance, a single pixel might require 24 bits, 8 bits each for red, green, and blue, to store its color information. This is where VNAND technology comes into play. Modern SSDs and smartphone storage use what's called charge-trap flash memory. Think of each memory cell as a tiny container that can hold different amounts of electrons. These electrons are trapped in an insulating layer, hence the name charge trap. The brilliant part is that these cells can maintain their charge for years, which is how your data remains stored even when your device is turned off. In the early days, each cell could only store 1 bit of information, either a 1 or a 0, depending on whether it held a high or low charge. But modern technology has evolved to allow multiple levels of charge in each cell. Today's memory cells can typically store 3 or even 4 bits of information by maintaining up to 16 different charge levels. This advancement has dramatically increased storage density while keeping the physical size of devices small. The vertical stacking of these cells is what makes VNAND truly revolutionary. Imagine building a skyscraper instead of spreading houses across a city. You're maximizing space by building upward. Current VNAND technology can stack anywhere from 96 to 176 layers of memory cells on top of each other. Each vertical stack or string contains multiple cells, and thousands of these strings are arranged in arrays to form memory blocks. But how does the system access specific bits of information in this complex structure? This is where the control gates and bit lines come in. Think of them as an elaborate traffic system. Control gates run horizontally through the stack, while bit lines run vertically. When data needs to be read or written, these gates and lines work together to activate specific cells while keeping others inactive. The organization of these cells is hierarchical. Individual cells are grouped into strings, strings are arranged into pages, and pages are combined into blocks. A typical modern NAND flash memory chip might have thousands of blocks, each containing multiple pages, and each page containing tens of thousands of cells. This organization allows for efficient data management and access. The speed at which modern SSDs can read and write data is remarkable. A typical SSD can transfer data at rates of 500 megabytes per second or more. This means it can read or write the equivalent of hundreds of high-resolution photos in just 1 second. This performance is achieved through parallel operations, multiple memory chips working simultaneously, and sophisticated controllers that manage data flow. One of the most impressive aspects of this technology is its reliability. Despite the incredibly small scale at which these components operate, we're talking about structures measured in nanometers. Modern SSDs can reliably store data for years. The charge trap design ensures that electrons stay where they're supposed to, even in the presence of heat or electromagnetic interference. The manufacturing process for these devices is equally fascinating. It involves hundreds of precise steps, including the deposition of various materials layer by layer, etching microscopic patterns, and creating electrical connections that are thousands of times thinner than a human hair. The entire process takes place in ultra-clean rooms where even a single dust particle could ruin an entire batch of chips. Looking to the future, storage technology continues to evolve. Researchers are working on new ways to pack even more data into smaller spaces. Some promising technologies include 3D X-point memory, which offers even faster access times, and quantum storage, which could potentially store massive amounts of data in atomic-scale structures. The impact of this technology on our daily lives cannot be overstated. It's what allows us to carry our entire music library in our pocket, store thousands of photos and videos, and run complex applications on our smartphones. The next time you snap a photo or download an app, remember the incredible engineering that makes it all possible. Layers upon layers of precisely controlled electrons, working together to keep your digital life organized and accessible. From the initial conversion of data into binary code, through the complex structure of VNAND memory cells, to the sophisticated controllers that manage it all, modern data storage is truly a marvel of human ingenuity. It's a perfect example of how pushing the boundaries of physics and engineering can create technology that fundamentally changes how we live and work.